you want some paper. Okay, so somewhere or other you're going to write out all the different types of reactions and an example of each. Now your example can be like a real example with real chemicals, or it can be like the sort of A plus B kind of thing if you prefer that. So just give that a try, see what you remember from last year, what you absorbed from the video yesterday. Okay. There we go. When we have a synthesis reaction, what type of reactants do we have? What are the types of things? Your choices are element or compound. What types of things are your reactants? Elements. You have an element plus an element. And when we react them together, do we write an equal sign? No, what do we write? We write an arrow, okay? And what do we get when we react that element and that element? We get a compound, yes. Now, when it comes to predicting the products, which we're not doing quite yet, but just to get you thinking about it, this is the only kind of synthesis reaction that you'll be expected to predict the products, okay? I'm never going to give you like a more complicated one. But if it's just if I give you a reaction and I just want you to recognize it as synthesis, I could give you two things. It could be a compound and an element, or a compound and a compound, and they react to form one thing. You would still need to recognize that as synthesis, although you would not be expected to predict the products. Okay, so that might be something like, for example, H2O plus CO2 gives H2CO3. I would not expect you to be able to predict those products, but looking at that reaction, you have two things becoming one thing. And so that is synthesis, even though it's not the stereotypical element plus element gives compound. Okay? So these ones you would need to recognize as synthesis, but you would not need to predict the product. But if I gave you the stereotypical element plus element, let's say I gave you, oh, what's a good one? Cl2 plus Na, that's an element and an element, yes? And for that one, I can expect you to be able to take those two elements and put them together into a compound. Like I said, we don't need to actually predict the products yet, but just so you get a flavor of what that's like, would it be okay for my product to look like this? I hope that you look at that and go, wow, that's really weird, Ms. Spence, don't do that. Okay, because that just looks so strange. What are the two things that are wrong with that? Yeah, the metal has to go first, right? So definitely not that. The metal has to go first. So what if I wrote NaCl2? Would that be okay? No, and the reason for that is why? Why is NaCl2 not a workable solution? Because the charges don't balance, right? Na is plus, Cl is minus, And so we would have to have it be NaCl. Okay, so that's just a flavor of what we're going to be looking at. So when we're predicting products, we're always looking to predict the actual correct formula, not just some random smashing together of letters, okay? All right, so that is synthesis. Two things become one thing. Like I said, if it's more complicated, you'll just need to be able to recognize it. Later on, when I give you two elements, you'll have to predict the products. What is the opposite of synthesis? Decomposition. What type of thing do we start with? We start with a compound. And it reacts to form two elements, element plus element. Now, in terms of recognizing, again, you could have a more complicated sort of recognizing thing. I might take some Na2CO3, and if it reacts to form NaO plus CO2, you would be expected to recognize this as one thing becomes two things, but this particular one you would need to recognize but not predict the products. Recognize as decomp. Okay, so you need to be able to predict the products for the standard single compound gives element plus element. You need to recognize that if you have one thing that goes to two things, that is decomposition, but you would not need to say, I know what happens when I have Na2CO3. I mean, I know what happens, but then I'm a chemistry teacher, right? I should know, but you guys would not be expected to, certainly not in grade 11, okay? But what if I gave you one like this, a more traditional one? What if I gave you, let's say, KCl? You would say, look, I have one compound there. What's the only thing that one compound can do? It can split apart. And what two elements does it split apart into? K and Cl. What do you guys think about those products? Are they like super happy products? Or could they use a little work? I want you to remember Dr. Brinkelhoff. What do we know about Brinkelhoff? Those are our diatomics. And that means when they are on their own, they are, what do I have to do here? I would have to put a 2 here. Okay, and that reaction as it is that a balanced reaction the way it is, or is it unbalanced? That's unbalanced. How could we fix it? This one's pretty straightforward. If you have 2 chlorines, you could put a 2 here, and that would give you 2 chlorines, but we've now changed the potassium to 2, and so there's going to be a 2 here. Don't worry if you're like, you expect me to just know how to balance? It's okay, this is just a preview. Again, we're gonna go through a whole bunch of tips and tricks of how to balance, okay? So we have synthesis, we have decomposition. Now we're balanced. What is a third type of reaction? Tell your partner, what's a third type of reaction? What's the one that starts with, the other one that starts with S? Single replacement. Now we actually learned in 2 types of single replacement yesterday. So A is single replacement non-metal, whichever way you want, non-metal. And if we have single replacement non-metal, what are our reactants? We have a non-metal plus what? Plus a compound. Okay. And then we will end up with a non-metal plus a compound. So the non-metal takes the place of the non-metal in the compound, okay? So for example here, we might have Cl2 plus NaBr. The non-metal replaces the non-metal. So basically, chlorine goes in and takes bromine's place and it kicks it out. So now what I have is I have sodium is not with bromine anymore. Sodium is with chlorine. So I have sodium, which is positive. I have chlorine, which is negative. And so I don't have NaCl2, right? I don't want NaCl2. I don't want Cl2Na. I don't want any of those weird things. I want the correct formula for sodium and chlorine, which is NaCl. And then bromine has been kicked out. So it's on its own now. What do we know about bromine when it is on its own? It's diatomic. Yes, Brinkelhoff. Okay, so bromine is diatomic, so we would put a 2 there. Is this a balanced or an unbalanced reaction? It's unbalanced. Right now, we have 2 chlorine and 1 chlorine. Should we start with chlorine? This one's going to be easy to balance, so we'll just start with the chlorine. What would we need to do? What do we have to add to the right-hand side to give me 2 chlorine on the right-hand side? we're going to put a 2 here, and that 2 then applies both to the Na and to the Cl. So now I have 2 Cls on both sides. By the way, what do we call that number that goes in front? Do you remember that? That number is called a coefficient. Hello. Oh, thank you. Okay, so that number is a coefficient. So we used a coefficient to balance the chlorine. Now we have 2 chlorine on both sides, but what did I mess up in that process? I now have 2 NAs, but over here I only have 1 Na. What could I do to fix that? I could add a coefficient of 2, which now means I have 2 sodium and I have 2 bromine. Do I have the right number of bromine on each side? Well, look at that. I got 2 bromine and I have 2 bromine. So everybody's balanced. Isn't that nice? So single replacement nonmetal, we have a nonmetal plus compound, gives a nonmetal plus compound. The nonmetal replaces the nonmetal. What's the other type of single replacement we have? Single replacement metal. And that would look like metal plus compound gives what would we get? Metal plus compound. Yep. Metal plus compound. So what if we had, like, let's say, CaCl2 plus, I don't even know, Na. Would I get CaNa plus Cl2? No. Because I don't put the metal with the metal. The metal has to replace the metal replaces the metal. So would I get NaCl2 plus Ca? What do you guys think? Yes? No? Maybe. It's one of those. What do you guys think about my products there? What is does the calcium look okay on its own like that? Is calcium diatomic? No. Okay. What about NaCl2? Is that a good formula? No, why not? Because I got a Cl2. Na is positive, Cl is negative. I only need one of each, so this is not correct either. I need NaCl plus Ca. We're not going to bother balancing this one right now. Well, we could. What would we need to do to balance it? We would need 2 NaCl because we already have 2 chlorines. Now we have 2 chlorines, but what else did we change when we changed that? We changed the 2Na, so we would need to put a 2 in front of the Na on the other side of the equation. A lot of balancing is really easy, okay? So the first ones we're going to be doing, the balancing won't be too bad, okay? We'll get into the trickier ones later, and I'll give you a lot of sort of useful ways of figuring it out. Okay, so that was single replacement. What would we like next? Double replacement, sure. Let's do double replacement next. And what kind of things do we have as our reactants in a double replacement? We have a compound, and we have another compound. And what do we get as products? Compound and compound. Oh. What type of compounds are these? They are ionic compounds, all of them, because the metals swap places and the non-metals swap places. Okay, so everybody is ionic. So we went from synthesis, where we had element plus element, decomposition, where we had compound, single replacement, where we have non-metal, which is an element plus a compound, right? This is an element plus a compound, or the metal version, where the metal is the element plus a compound. And then finally, we're getting down into the double replacement, where we have the compound plus the compound. Now, going to give you a little example here and show you how we will predict the products when we get into this later. Let's say we have PB NO3 2 plus Ki, compound plus compound, both ionic compounds. I think it's in section 6.4, we're going to predict the products, but right now we're going to give it a try just so you get a preview. What you're going to do is you're going to write out all the ions that are present. Who is the positive ion in PbNO32? Who's the positive ion? Pb. We have Pb 2 plus, and the negative ion is NO3 minus. Who's the positive ion in Ki? K. And who's the negative ion in Ki? I. And what we're going to be doing is we're going to be, step 1, combine the outside ions and what do I mean by outside ions? I mean the two that are on the far sides. Okay, they're on the outside, yes? Those are our outside ions, the Pb and the I. The K and the NO3, those are our inside ions. So outside ions, inside ions, outside ions, inside ions. Do it with me. Outside ions, inside ions, outside ions, inside ions. So first we combine the outside ions and we go forward. We go from left to right. The reason we do that, we go from left to right, is because we want in all compounds our positive ion should go first. So we're going to say lead is going first and then iodine is going second. What is the correct formula for Pb2 plus and I minus? We get Pb I2. Now we're going to do our step 2, combine the inside ions. And instead of going forward from left to right, we're going to go backward from right to left. Why are we doing that? Why am I going backward this time? So the K, the positive ion, ends up before the negative ion. So I want the K to go first, and I want the NO3 to go second. So we end up with, and they're both positive and negative 1, so that's just going to be KNO3. Here's a little tip for balancing when you have polyatomic ions. You might remember this from last year. You can make life a lot easier on yourself. Don't balance the N's and O's separately, but treat this entire thing as a little group. How many NO3s do we have on the right-hand side? Right now, we just have one NO3. But on the left-hand side, how many do we have? We have two NO3s. So how could I fix that? I could put a 2 here. So that's going to give me 2 NO3s, but it's also going to give me 2 Ks. But I can fix that, right? Because over on the left, right now I've got 2 Ks on the right, but I only have 1 K on the left. How can I fix that? I can just put a 2 here, and we're all good to go. And if you're freaking out, you're like, oh my God, do I have to do this all now? No, we're going to work our way up to you being able to do this independently, okay? All right, so that was double replacement. There's 2 more types. I want to pick neutralization next because it fits very nicely with double replacement. They're almost like the same, okay? Neutralization. This one's a little more specific. We can't just say it is still compound plus compound gives compound plus compound, but there's specific types of compounds. Do you guys know what they are? We have an acid plus a base, and my products are a salt plus water. Now that's very nice, but well, what does that mean? What does an acid look like? How do we know we have an acid? It starts with H, or ends with not just H, but COOH. Okay? So it either starts with H or it ends in COOH. How do we know that we have a base. A base ends in OH. It contains the hydroxide ion. It's different than COOH. We'll talk more about that distinction later. There are OHs that are in alcohols that are not hydroxide. It contains hydroxide, which is OH minus. Now, what the heck is a salt? A salt is just an ionic compound. So yeah, NaCl is a salt, but PbNO3 too is also a salt. It's an ionic compound. Na2SO4, ionic compound, salt. MgCO3, ionic compound, salt. Okay, so a salt is an ionic compound. And water, of course, we know is H2O. Let's take a look at an example. H2SO4, we know that's an acid because it starts with H. We're going to react that with NaOH. And we know that's a base because it ends in the hydroxide ion, OH. Okay, so we've got our H and we've got our OH, so we know that that is an acid plus a base. Now, neutralization is just a special type of what other type of reaction? Double replacement. Are we good with DR for double replacement? Okay. How did we predict our products when we did a double replacement? What was step one? Combine the outside ions, and step two was combine the inside ions. So let's look at doing that here. Who is the positive ion in H2SO4? H. And what is its charge? Just plus. Okay, so +1. And then, of course, we have SO4. And we can look up its charge. It is 2 negative. The positive ion in NaOH is Na plus. And the negative ion is OH minus. So we are going to combine our outside ions going forward. So the H comes first and the OH goes second. So these are our outside ions. And I'm going to do something a little bit weird. I'm going to write my H and my OH separately. I'm not going to write it as H2O. Bear with me here. There's reason behind my madness. Okay. My other product, what am I going to combine? I combined the outside ions. Now I will combine the inside ions. Do I do that in a forwards direction or a backwards direction? Backwards direction. So Na is going to come first because our cation always comes first. SO4 is going to come second. What is the correct formula for a compound made of Na plus and SO4 2 minus? Na2SO4. Na2SO4. So that is our salt that we have formed. Now, in terms of balancing, when you're balancing neutralization, you're going to balance the salt, the ions in the salt first. So who are the ions in the salt? Here is our salt. And it is made up of Na ions and SO4 ions. Do we have a different number of SO4s on either side? Or do we have the same number of SO4s? We have the same because we got SO4 here and we have just one SO4 here. So that looks pretty good, yes? One SO4 on the left, one SO4 on the right. How about the Na? Not so good, right? Because right now we have two NAs. And over on the right, we only have one Na. How can we fix that? Put a 2, put a coefficient of 2. And now you're going to see why I left my water as HOH, because at this point, once you've balanced the ions in the salt, you can balance either the hydrogen by itself or the hydroxide. We're going to say we're going to balance the hydroxide as a group. How many hydroxides do we have on the right? How many? 2. Yes, because we put that coefficient in front. Oh, I meant on the left. I meant on the left. Yeah, that the other right. Yes, the left. How many hydroxides on the left? 2. How many on the right? Only 1. So what do we need to do? We're going to put a 2 there, and that means that now we have 2 hydrogens, and we have 2 hydrogens, and everything is lovely. Sometimes if you put it as H2O, you can get kind of lost in the H's and the O's because they get mixed up together. But if you leave it as HOH before you balance it, you can always change it later into H2O. Balancing neutralizations becomes really easy. Okay. All right, so that was neutralization. And we had one last type of reaction. And what was that? Combustion. And this one is very specific, right? Predicting the products is actually the easiest for this one because it's only ever the same thing. What do we start with? We start with a hydrocarbon, which is a compound that contains which 2 elements? Hydrogen and carbon. So we're going to have, and that we usually write the carbon first, almost always. C, and we don't know how many. And we have H, we don't know how many. And you might have another element or 2, okay? But you're going to recognize it. You'll be like, CH. Good. Now, sometimes you might have CH3COOH, and that's an acid, and maybe you have a neutralization, but this one will not only have a hydrocarbon, it will also have, who's the other thing needed for things to burn? Oxygen. And what is the formula for oxygen? O2. What do we get as our product? CO2 plus H2O. And if you ever have problems remembering those 2 products, your body burns fuel, yes? And what do you breathe out? You breathe out water, because if you breathe on the, like on a window in the cold, you see the water there. So you breathe out water. What else do you exhale? You breathe out water and you guys don't know that you exhale carbon dioxide? You did not know that? Was that new information to you? No, you guys already knew that, right? Yes. Okay, and if you didn't, you know now. Okay, so that is combustion. And so it's really easy to predict the products because it's always carbon dioxide and water. So those are our 6 types of reactions. Would someone like to hand out the little cheat sheet? Not that you get to use it on a test. Thank you. This is like a little cheat sheet for recognizing reaction types. So if you're working through, part of today's homework is going to be 6.2a, where you're classifying the reactions. You can use that to help you out. But we are going to not do that right now. We're going to go to 6.1c, which is on page 14. There's a video that goes along with this, but I feel like it takes a long time to go through some really basic stuff, so we're just going to jump into it. What symbol is used to separate the reactants from the products? That is an arrow, not an equal sign. Now, when we're writing a chemical equation, instead of writing H2 and O2, we would replace the and write a plus. Excellent. To accurately represent the number of particles taking place in a reaction, we write numbers in front of the molecules. What do we call those numbers? Coefficients. Now, this one actually does rely on the video a little bit, so what I'm going to do is I'm going to draw the little reaction myself here. Okay, so we have H2 plus O2 gives H2O. So that is a chemical reaction. That's the one that we looked at last day. And the question asks, are the number of molecules conserved? Is the number of molecules that we start with the same as the number of molecules we finish with? Molecules. How many molecules in the reactants? 1, 2, 3. How many molecules in the products? 1, 2. Are the number of molecules conserved? Are they the same before and after? No. Our next question, though, is, are the number of atoms conserved? Does the number of atoms before equal the number of atoms afterwards? How many atoms over here? 2, 4, 6. How many over here? 1, 2, 3, 4, 5, 6. 6 atoms and 6 atoms. Yes. So the answer is yes, atoms are conserved. And what about the next question? How about the atoms of each type? So are the oxygen atoms staying the same? Is the number of oxygen atoms staying the same? Yes. Is the number of hydrogen atoms staying the same? Probably. Well, let's count them. The hydrogens are the little white ones. 1, 2, 3, 4. And then over here we have 1, 2, 3, 4. Oh my gosh, they did. Okay. So yes, the number of atoms stay the same. And all of this is leading us to the law of conservation of mass. What is the law of conservation of mass? Do you guys know this? It can neither be created nor destroyed. So when we talk about conservation, we're talking about keeping it the same. So in other words, the atoms, the number of atoms of each type stay the same, but they bond to each other differently. The number of atoms of each type stay the same. They just bond to each other differently. So here we have a word equation, which I'm really regretting having in here. But this was from the year when we didn't get to do reactions because it was the quarter system. So I sent people off to go watch the videos on their own so that when they arrived in Chem 12, they would not be bumbling idiots. But that's okay. A word equation just means you write the words. Hydrogen plus oxygen gives water. That's the word equation. We can replace those words with formulas to write the formula equation. Okay, so we now have, instead of hydrogen, we have H2. Instead of writing oxygen, O-X-Y, blah, 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 we write O2, and instead of water, we write H2O. Now, right now, we have 2 hydrogen atoms. We have 2 oxygen atoms on the, what do we call those things that are on the left-hand side? These are the reactants. So we have 2 hydrogens and 2 oxygens in the reactants. What do we call the thing on the left? That's called the products, because they are produced. We have 2 hydrogens. Oh, so far this is looking good. 2 hydrogens, 2 hydrogens. But what's wrong with this picture? We only have 1 oxygen. Oh dear. Can we fix this problem by adding a subscript? No, because that would turn our lovely water into hydrogen peroxide. Water, lovely to drink, hydrates you, yes. Hydrogen peroxide, you pour it on a wound and it bubbles and turns your skin white. Okay, and like destroys the tissue, essentially. Yes, the reason they use hydrogen peroxide on wounds is because, yes, it does kill bacteria, but it also kills your cells as well, which is why it's not the preferred method of dressing a wound is to use hydrogen peroxide, but you can. It's kind of fun, bubbles all over, but it's not the preferred method anymore. Peroxide. So we cannot change the actual compound. So no, we cannot do this. How could we do it? What are you? What? I just heard the H. What about the H? Add a coefficient, bless you. Okay, if we add a coefficient, where should we add a coefficient? In front of H2O, yes? Because that's going to now give us, instead of one oxygen, we're going to have two oxygens. Bless your heart. But what has happened now? I've changed that to two oxygens. What else have we changed though? We have 2 times 2 is 4 hydrogens. Uh-oh, we fixed oxygen, but we messed up hydrogen. What could we do to fix hydrogen? We could add a 2 here. Now we have 2 times 2 is 4 hydrogen. Now we have 4 hydrogen on the left, 4 hydrogen on the right, 2 oxygen on the left, 2 oxygen on the right. Yay! And a lot of them really are that simple. Okay, a lot of the ones you'll be doing right away will be quite simple. All right, so we're just going to leave that, blah, 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 blah. So we have an unbalanced equation. We've created a balanced equation. On the next page, I would like to draw your attention to the word formula versus equation, because in like math, maybe in physics, sometimes we might use those terms interchangeably. But in chemistry, the formula refers to the chemical formula for an element or a compound. So NO2 is a formula. O2 is a formula. Fe is a formula. This is the formula for ammonium carbonate. So those are all formulas. That's as opposed to an equation where we have the reactants, we have the products, and we have that arrow sign in between. Yes? So the equation is where we have the reactants. Oops, that was supposed to be a pen. We have the reactants, and we have the products, and we have the arrows in between. That's an equation. One of the most common mistakes that students make is to use an equal sign. This is a very common error. No, 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 no. Sad face. Okay, do not do that. I've got someone hiding outside my door and ducking down as though I did not see her. Gone now? Okay. Alrighty. So I decided in my last block that I did not like how this was done. Okay, so we're going to cross out word equation because I actually don't feel like there's a huge amount of value in writing the word equation, because you've done some of that last year and it just kind of, so we're just gonna cross all of this out, and we're going to use this space. We're going to use this space to write the balanced reaction, and we're going to start by looking at who our reactants are. Take a look at that sentence there. Aluminum metal combines with bromine to form aluminum bromide. Who are our reactants? Aluminum is a reactant and bromine. So we're going to write the formulas for aluminum and bromine. Aluminum Now, do I write 3 plus? No. Elements on their own have a charge of 0. Okay, so that's aluminum. That's neutral aluminum. Now it reacts with bromine. So I put plus Br. What do I have to do? Br2. We want to make sure that we get our formulas correct. Those react to form aluminum bromide, AlBr. No? What's wrong with that? Well, when it's in a compound, what is the charge of aluminum? 3 plus. When it's on its own, it has a charge of 0, but when it's in a compound, it has a charge of 3 plus. And what's the charge of bromine when it's in a compound? -1. So it's not just Al, it's AlBr3. And I'm going to give you tip number 1. If you have a 2 and a 3, like right now, let's just write out a little chart down below. We have right now 1 aluminum, and we have 2 bromines over on the left, and we have 3 bromines over on the right. If you have a 2 and a 3, of the same element, find the lowest common multiple, which is 6. So instead of having 2 bromine, instead of having 3 bromine, we're going to make sure that we have 6 bromine. When you have a 2 and a 3, that's the only way to balance them, is to have 6 of each. So let us see if we can get 6 bromine on the left-hand side. What do we have to do to get 6 bromine on the left-hand side? We have to put a 3. So that's going to change this bromine, the number of bromines, to a 6. And we haven't changed anything else because that was an element. On the right, what do we have to do to get 6 bromine? Put a 2. Okay, and that's going to change my aluminum, though, as well to a 2, and my bromine to a 6. So what can I fix? What do I have to do to fix it completely? I have to put a, 2 on the left side in front of the aluminum, and now everybody is the same. 2 aluminum on both sides, 6 bromine on both sides. Okay. And now we're going to go here. When you're writing these, we're going to do a couple together before I send you off home. You're going to leave room for coefficients. You're going to remember your diatomic elements. I want you to highlight these or put a star beside them for yourselves. Sulfur is S8 and phosphorus is P4. Why? I don't know. They just are. Okay? So let's try a couple of these, and we're just going to ignore this bit here, okay? We're just going to do it the way we did the last question. So you can just kind of scribble that out there. We have zinc metal and sulfur powder. Those are our reactants. So what am I going to write? For zinc metal, I'm going to write Zn 2 plus, right? No, why not? Elements on their own are neutral. And I have sulfur powder. Now remember, sulfur was one of those little bizarre ones, S8. And they form, remember this is an arrow, not an equal sign. They form zinc sulfide. ZnS8, right? Am I correct? No, because what is the charge of zinc? In a compound, it's 2+, sulfide is 2-, so I should actually have ZnS. Okay? Now, I have 1 zinc, and I have 8 sulfur on the left. On the right, I have 1 zinc, and I have 1 sulfur. How can we fix that? On the right, we need a coefficient of 8, which changes both the sulfur and the zinc. So now we need to correct the zinc on the left by putting an 8 in front of it. And now we are completely balanced. Okay, again, ignore this bit here. I'm going to rewrite these so they don't have all the little bits on them. We have aluminum metal, so that's just going to be Al, reacts with hydrogen monochloride. What on earth is that? It's just H monochloride Cl. It reacts to yield. To yield means to give, so arrow. Aluminum chloride plus elemental hydrogen. Do you like my aluminum chloride? No, why not? Al in a compound is 3+, chloride in a compound is negative, so it should be AlCl3. So I'm good now, right? No. What's wrong? Sprinkle Huff. Okay, we need to have an H2 because hydrogen is one of the diatomics. Okay, so we now have on the left-hand side, we have, I didn't leave really enough room here, but that's okay. We have 1 aluminum, we have 1 hydrogen, and we have 1 chloride. We'll make it work that way. On the right, we have 1 aluminum. How many chlorine? 3. Yes, chlorine. And how many hydrogen? 2 hydrogen. We can pick whichever element we want to start with. Do you have a preference? Well, aluminum's done, so we're not going to pick aluminum, but we could let's start with chlorine. Okay? I have 3 chlorine on the right, so what do I need to do on the left? I need to put a 3. But that changes both the chlorine and the hydrogen. Now I want you to take a little look here. We now have 3 hydrogen on the left and 2 hydrogen on the right. What do we do when we have a 3 and a 2? We want to go for 6. Okay, so we're going to try and get 6 hydrogen on each side. So what do I have to do here to get 6 hydrogen? I just have to get rid of that 3, yes, and replace it with a 6. So that's going to give me a 6. And how do I get 6 hydrogen on the right? I put a 3 in front of the H2, And don't forget, I changed my hydrogen to 6, but I also changed my chlorine to 6. So if I want chlorine to be 6, I need to put a 2 here, which changes chlorine to 6, but it also changes aluminum to 2. All right, and we now have 2 aluminum, so we need to put a 2 here. That's as bad as it's going to get for now, okay? What I would like you to do for homework is I would like you to do questions 3, 4, and 5. Okay, so 3, 4, and 5. And then I would like you to do 6.2a. Okay, so do number 3, 4, and 5. That's on pages 16 to 17. The homework will say 3 to 8 because my morning block had 20 minutes to work on this. I don't know how we managed to go so much faster in the morning, but that's okay. So you can just ignore the 8 unless you want to do the extra practice. And you're also going to do 6.2a, the exercises. That's that Tyler DeWitt one. Now you're going to classify them. Okay? Those don't take very long.